Hey everyone, welcome to The Explainer. If you're the kind of person who really wants to understand the mechanics of the world around us, you are in the exact right place. Today, we're taking a journey from the microscopic, totally invisible world of a single electron all the way up to the heavy-duty, everyday appliances we rely on. We're going to unpack the literal building blocks of electricity, circuits, and Ohm's law. So let's ground ourselves in reality for a second before we get into the heavy science. I want you to ask yourself, what exactly is the invisible force powering the device you're using to watch this right now? I mean, we flip switches and plug in chargers every single day without even a second thought, right? But underneath the casing of your phone or your computer, there's this highly orchestrated mathematical flow of tiny particles just working around the clock. Here's our roadmap for today. We'll start with the nature of electricity, then we'll build a simple circuit. After that, we'll dive into the rules of Ohm's law, and finally, we'll wrap up by calculating the flow. All right, part one, the nature of electricity and the raw materials of power. Before we can even think about building a circuit, we gotta understand what's actually flowing through it. We define electric current simply as charges in motion. Basically, it's just the rate at which charge flows past a specific point. You can kind of think of it like water flowing through a pipe. But for this charge to actually move, it needs a push, right? And that push happens whenever voltage is applied. The little subatomic particle responsible for all this current, that's the electron. Now get this. The astonishingly tiny number of negative 1.602 times 10 to the negative 19th coulombs, that is the exact electrical charge of a single invisible electron. It's wild. To get just 1 ampere of current, which is our standard unit of measurement, you literally need a massive, almost incomprehensible amount of these tiny electrons flowing past a point every single second. When we track this movement, we actually use two different maps. Conventional current describes the flow from the positive to the negative terminal. Funny enough, this is actually what early scientists guessed before they fully understood electrons. But then we have non-conventional current, which tracks the true physical reality. In reality, those negatively charged electrons actually flow from the negative terminal to the positive terminal. Kind of backwards, but that's how it works. Moving on to part two, building a simple circuit and setting up the track for our electrons. Every basic circuit construction project requires 4 simple components to give those electrons a closed loop to move through. First up, you need a voltage source, like a battery, to give that initial push. Second, connecting wires to act as the highway. Third, you need a switch to actually control the flow. And finally, a load, something like a light bulb or a resistor. That's the device that's actually putting all that electrical energy to use. When those 4 components come together, they create a perfectly working pathway. The battery provides the voltage, and the electrons travel through the connecting wires. They then pass through the light bulb, which causes it to illuminate, and they just continue on their journey right back to complete the loop. Without this continuous closed loop extending from one terminal all the way to the other, well, the bulb simply isn't going to light up. And that brings us to a super important distinction when we're actually operating a circuit. Think of the circuit switch like a drawbridge on a castle. An open circuit means the switch is open, which creates a physical gap in the conducting wire. The drawbridge is up, so the flow of electrons is completely stopped. There's no way across. Conversely, a closed circuit means the switch is closed. There's no gap, the drawbridge is down, and the traffic of electrons can move freely to light that bulb. Now, if we manipulate this pathway, we can completely change the flow. Imagine a basic closed circuit, but then we decide to add a resistor into the mix. A resistor acts exactly like a narrowed road on our highway. It intentionally creates a bottleneck, a hindrance to the flow of charge. So it literally slows down the electrons, which in the case of our light bulb would result in a dimmer light. We're controlling the traffic. All right, part 3, the rules of Ohm's law, or as I like to call them, the traffic laws of circuits. Ohm's law is absolutely crucial here. It's the ultimate traffic law for electricity. The rule basically states that electric current is directly proportional to the voltage and inversely proportional to the resistance. In plain terms, it brilliantly links the push of the battery to the narrow road of the resistor. It tells us exactly how much current is going to result from that specific combination. But before we get into the hard data, I want you to actively think about this for a second. Take a guess. What do you think happens to the electron traffic when we keep our narrow road, the resistance, exactly the same, but we push twice as hard with our battery voltage? Any ideas? Well, the answer lies in the numbers. Let's say we double the voltage from 1.5 to 3 volts, but we keep the resistance totally steady at 3 ohms. What happens? The current doubles right along with it, jumping from 0.5 to 1 amp. That is direct proportion right there. But on the flip side, what if we keep the voltage at 1.5 volts, but we double the resistance from 3 to 6 ohms? We're squeezing that traffic, right? So the current gets cut exactly in half, down to 0.25 amps. And that is inverse proportion in action. Which leads us nicely into part 4, calculating the flow and doing some everyday problem solving. Ohm's law gives us these 3 incredibly powerful, but honestly very simple mathematical formulas. The magic here is that if you know any 2 variables in a circuit, you can always find the third. If you need to find the voltage, you just multiply current times resistance. So V equals I times R. If you need current, it's I equals V divided by R. And for resistance, it's R equals V divided by I. By just swapping between these 3 variations, you can easily calculate the missing puzzle piece for literally any electrical device. Let's walk through a concrete example. Say we want to determine the current flowing through a standard circuit, and we already know the voltage and resistance. We just plug our numbers into that I equals V divided by R formula. So taking 3 volts and dividing it by 3 ohms of resistance perfectly calculates that exactly 1 amp of current is flowing through that system. Super straightforward, right? Now let's actually apply this to something you probably have in your kitchen right now, like a high-powered air fryer. The math holds up perfectly here too. Step 1, we identify what we know. A standard wall outlet usually provides 220 volts, and let's just say this specific air fryer draws a current of 4.2 amperes. Step 2, we need to find the resistance inside the machine, so we grab our formula, R equals V divided by I. Step 3, we divide our 220 volts by those 4.2 amperes. Doing this lets us discover that there are roughly 52 ohms of resistance happening inside that machine just to cook your food. How cool is that? So as we wrap up today's explainer, I want you to do something for me. Take a second and just look around your room right now. Can you picture it? Can you actually envision that invisible, mathematically perfect flow of billions upon billions of electrons? They're being pushed by voltage, they're being slowed down by resistance, and they're moving in this perfect, continuous loop just to power your lights, your computer, and basically your entire modern life. It's not magic, guys. It is the predictable, absolutely fascinating science of electric circuits and Ohm's law hard at work. Thanks so much for learning with me today. And hey, keep questioning the world around you.